Yeah, good morning. So, today we will start a new topic known as Laplace and Poisson equations. We will try to understand these two equations, Laplace equation and Poisson equation. And what we have completed so far, the first order equations. In the first order equations, we have given a general theory, but then we also introduce what is called classifications. And now you know that the partial differential equations can be classified into elliptic, parabolic and hyperbolic. Okay. All these three categories have different behavior. So, studying the equations in general is a little more difficult. So, what we are going to do is to study a representative equation. So, what we are planning in these 5 to 6 hours of lectures, even then we will not be able to complete much, we will do only a part of it. The remaining part of this will be seen in the next course, not even in this course. Okay. So, let me write down second order elliptic equations, Laplace and Poisson equations, Laplace and Poisson equations. So, how is the general second order linear? General second order linear. The general form is sigma aij of x d square u by dxi dxj xi xj. I am just recalling what you already know here. Sigma ai of x du by dxi plus a naught of x u equal to f. This is the general form of equations. Here I j varies from 1 to n, here is I, that is it. This is elliptic, so I am just recalling, elliptic if summation, we do not write summation all the time if there is a repeated indices is used, psi I, psi j is greater than or equal to alpha into mod psi square. If there exists alpha positive such that this is true, then it is called a elliptic operator. An important elliptic operator is Laplacian. Okay. So, if you take aij equal to delta ij, that is equal to 1, if I equal to j equal to 0, I equal to 1, if equal to 0, if I not equal to 0, not equal to j, and ai equal to 0, a not equal to 0. So, this is let me write down the elliptic equation, L of u equal to, that is the operator L of u. That implies my L is equal to the operator Laplacian. Laplacian means summation d square by dxi square. Okay. So, I want to study, so the purpose of this course is to understand the equation, understand the boundary value problem, minus Laplacian of u, minus we use it for some reasons, but you can also use it without minus omega, because minus Laplacian gives you the positive definite operator in some sense. So, let us not bother, and u equal to g and omega. So, our aim is to understand this problem, understand the boundary value problem, or rather you want to understand the solvability. It is not an easy thing. So, studying the Laplacian problem instead of a general theory, there are twofold. There are two reasons, there are many, but two important reasons why we are studying first Laplacian. This Laplacian operator appears in large number of applications. Okay. So, it is not that this operator is just an example, it is a part and parcel of any differential operator theory, and in any physics, lot of physical and engineering applications, this Laplacian operator appears frequently. So, and this study of this is called the potential theory. Potential theory. The second reason for studying it is a very particular example. It is not just particular example, it is also a prototype. Laplacian is a prototype of general second order, prototype of general equation. What do you mean? What do I mean by general equation? Prototype means this Laplacian, even though it looks like a very simple operator, it has many features of general general operators. So, the study of general equations is called the Schauder theory. Schauder theory, and it is, so if you want to understand the general second order operator and its boundary value problem, instead of Laplacian you want to study Lu equal to F with U equal to G. But then even to understand this equation, understanding Laplacian operator is important, and through the lectures you will see that even to get various properties and solvability of Laplacian itself is a challenging problem. It is not easy. That is that even in the 5-6 hours I can only state certain properties and maybe solvability in very special cases. So, the general solvability we will only discuss it in the next course as and when that happens. Okay. So, that is the reason why we study Laplacian operator. Okay. So, let us go to the case now. It appears in various ways. Okay. One more thing before I go further, just like Laplacian is a prototype of an elliptic equation and we are spending time on understanding this equation, you will also study the heat operator, which is a representative of the parabolic class, and you study wave equation, which is a representative of the hyperbolic equations. So, basically now the rest of the course will be studying these three equations, its solvability questions, its properties, and various things related to these three equations. So, let us go to some physical interpretation. Let me give you very general physical interpretation. Physical interpretation. Okay. It is a very general interpretation, you can solve it as I said here. Suppose U is a density, some density of some quantity. So, that is what I say, it is a very general physical density, and F is the flux density, flux density. And you have your equilibrium state, equilibrium state. Okay. On equilibrium, so you have your domain omega and you take any V. Since it is in equilibrium, the it satisfies the flux through any small region. So, you take a small region, look at its boundary and look at its flux across the boundary. This has to be 0, where nu is normal, where nu is normal, unit normal. Now, you know that in our preliminaries we have introduced you what is that one, f dot of nu equal to 0. Now, you apply your divergence theorem. This is nothing but integral over V over divergence of f equal to 0, and this is true for all open V contained in V. These are all some simple analysis. So, when open V contained in N, then this will imply your divergence of F equal to 0. Okay. This is the equation basically flux density. But in many cases F will be proportional to the gradient, will be something like A grade U. If that is the case, you get divergence 0 is equal to divergence of F is nothing but you get a Laplacian of U. That implies Laplacian of U equal to 0. So, Laplacian of U equal to 0 is called the Poisson equation, and if you have some external forces, you get Laplacian U equal to F. So, that is how the general thing comes into picture. Okay. All right. You can give other so many other physical interpretations, but let me not get into that one. So, what am I aiming this in this course? So, we are want to derive certain what I want to introduce in this course, what is called the concept of fundamental solution. Okay. Mean value theorem or mean value property. Okay, we call it MVP, and you derive some maximum principle and this leads to what are called the uniqueness result. And then we will introduce Green's function, and then Green's formula. This is what basically I want to do that. As I said, I am not going to study the existence in general, but in the on the way en route we will see some existence results, and we see also the construction of Green's function in some cases. Okay. And as because obtaining Green's function itself is a difficult job. So, let me do one by one. So, first we want to go to what is called a fundamental solution. First we try to understand a property. Okay. First we want to understand the spherical symmetry of Laplacian. So, let us understand one by one. Spherical symmetry of Laplacian. What is this approach? Suppose Laplacian of U equal to 0. That means, so whenever U satisfies Laplacian equal to 0, then U is called harmonic. Okay. U is called harmonic. And this is called the Laplace equation. Okay. So, let me set the names here. Laplace equation, and Laplacian of U equal to F is called the Poisson equation. This Poisson equation. Okay. So, you have Laplacian equation. So, what is this spherical symmetry? Suppose U is a Laplace is harmonic function, that Laplacian of U equal to 0, and let R be an orthogonal matrix. Let me not put it that way. R be an orthogonal matrix. Rotation. Orthogonal means orthogonal matrix that is rotation. R transpose equal to identity. Define V of x is equal to U of R x. So, that means R is a rotation, it rotates the vectors, you know it, right. If you have a vector here, it rotates along that. So, this is x, R x may be somewhere here. So, you have rotation. So, you are defining the value of the function by rotating. Then the exercise which I want to give you, this is your exercise. So, let me put it in a color so you can prove it. Then V is also harmonic, you see. So, this is what your spherical symmetry. So, if you have a function u and if you rotate, and that rotated function is also a harmonic function. So, this motivates us. So, this is the motivation which motivates us to look for a solution also symmetric, motivates to look for a solution, motivates to look for a solution which is radial. Radial means which is radial. So, we are looking for a solution as a one variable function R is equal to some sort of a something like of this form, u of mod x. Mod x is equal to R. So, that the value does not change, because Laplacian when it rotates does not change. You expect, you are not sure, the differential operator has a property, immediately it will transfer to the solution, but that is the least we can expect. By rotating your solution, you are getting another solution. So, you right from the beginning assume that the function u is independent of the rotation. That means it does not change when it rotates, it will change only if the radially it is changed. That is what I am saying, the function v of r is u of mod x. Then you can you want to compute then your Laplacian of u. How do you compute your Laplacian of u? So, I will leave it as a small exercise here. So, if you want to study this topic, for that matter any topic, you want to compute your du by dxi. So, you write everything, if it is a u is equal to, if your u of x is equal to u of xi, you can write it as a u of dr into dr by dxi, right, this you know. So, that is a u of mod x if you have it, if it does not depend on that. But how do you calculate dr by dx? R square equal to, so you have 2r into dr by dxi equal to xi, 2xi. So, that means dr by dxi is equal to xi by r. Use that to prove this is equal to v double prime of r, this is the exercise, okay, plus n minus 1 by r into v prime of r. So, you want to solve this equation, okay, solve it. So, that is your exercise. So, I will give you the idea, solve, that is your exercise, okay. That is it. But this is an easy second order equation. How do you solve it? I am giving you the steps, you just complete it. Put w of r is equal to v prime of r. That implies w prime of r plus n minus 1 by r, w is equal to 0. This is a first order equation, solve it, you can solve. So, first to solve your W and then solve for integrate to get your V. Okay. So, you get your V prime of r. So, you can solve it. Okay. That is exercise, you can do it. So, with that let me write down the solution immediately. So, we get do this, you if you want to study this course, is better do this kind of small exercises as and we proceed before you are reading further things. You get V of r is equal to, so V r of r, so you have to solve it separately. B and this is a second order equation. So, you will have two equations, log mod x or log r plus some c if in the 2 dimensional case, and this is equal to some b by r power n minus 2 c if n greater than or equal to 3, where b, c are constants, c are constants. Okay. Now, we choose special b and c, we choose, you will see later as we go along, special b c to define, okay, phi x equal to, the special b and c are chosen, it will become clear as we proceed further. You can choose other constants, but then there are reasons why we choose b and c as thing. I choose c to be 0 and here I choose minus 1 over 2 pi log mod x, and here this is if n equal to 2, and here 1 by n into n minus 2 n into n minus 2 into omega n mod x power x power n minus 2 if n greater than or equal to 3. Okay. So, you have this one, is better to remember this. Then the definition, phi is called the fundamental solution, called the fundamental solution of minus Laplacian. Be careful here, some books use Laplacian, in that case you may have to change the sign minus and here you have to put a minus a. Right now both are positive, when x is small you get, that is where the singularity is there. So, you are started with this, so if you go for it, so if you if you yeah, let me go to previous page, let me so if you look at it, you started with the solution of look for a solution. So, you want to look for a solution minus Laplacian of u equal to 0. By looking for a solution u, not a general solution, by looking for a solution u as a special form, as a special form of a radial solution, you arrived at the function phi x, you got it as a solution. So, you have but look at it, this has a singularity, phi has a singularity. So, phi has a singularity at the origin. Okay, you have a singularity at the origin. So, quite often singularity is a source of information, singularities are source of information. So, you do not want to miss it, source of information. And importantly, Laplacian of phi. So, you are looking for a solution in Rn, but then you have a singularity you think, but except that that singular point Laplacian of u equal to 0, this is a point wise thing, Rn minus 0, that is true. So, phi is harmonic here. So, phi is harmonic in that removed point 0 removed Rn, okay, is harmonic. Not in entire Rn, you got a function which is a solution to Laplacian Poisson equation, but then the solution is radial, depends only on the radial direction, which has a singularity, and it satisfies the Laplacian equation except at that point. So, strictly speaking, this fundamental solution is not a solution, but still we call it a fundamental solution. Now, as we go in these lectures throughout this course on Laplace equation, you will see that phi is used to construct solutions. Even though phi is not a solution, it used to construct. So, that means the singularity contains lot of information. So, and we want to extract the information contained in phi at singularity, at all the singularity. So, you can change this direction now. So, you fix y, fix y in Rn. I can define x going to phi of x minus y, okay. Then again this function, this is, so phi Laplacian of with respect to x to represent phi x minus y equal to 0 in Rn minus y, you see. So, you are trying to look for singularity. So, you want to have phi, you have a singularity at the origin. Now, you are shifting this point to another point and looking at the singularity. So, basically we are trying to look at the kind of information carried out on all the points there, and we want to see how this function reacts to another function. These are all have more physical motivation, let me not get into that. So, suppose f is another function, suppose f is a given function, f is a given function, then look at this function x going to, this is a constant now, f of y is a reaction phi acting on that, not really acting, it is a point, right, it is a product, you will see the action later. So, this is also harmonic, is harmonic. So, you want to combine all your singularity actions, and that motivates us to define what is called your summing all the information singularity. So, every point if you shift it, you have a singularity, phi of x minus y is harmonic except at that point. You take a finitely many, sum it, you still get a harmonic function except at that finitely many points. So, you do this a kind of infinite summation and intuitive picture, and you introduce an integral called phi of x minus y. So, you define integral of phi of x minus y summing all the singularity, and I call this to be ux, okay. I do not know, you need to have conditions to whether this is finite or not. So, there are questions you can ask that we will answer soon, okay. So, we will do and ask such questions, but what is this is called the convolution of f and g, convolution between f and g, f and phi, and that is denoted by phi convolution f, okay, this interaction is dy, this is an Rn. I am not sure this has a finite value, this is meaningful, but let us symbolically introduce and the convolution operator. So, let me do something blindly. I want to compute minus Laplacian, compute Laplacian of u. Suppose I can take inside, this is a question, now big question, can I take my Laplacian, this is with respect to x, can I take my Laplacian x phi of x minus y, there is no x here, f of y equal to 0 dy. But then this is 0 except at one point, right, except at so when you have a function which is 0 except at one point, except at y equal to x, then integral has to be 0. So, it looks like that we got a solution. So, that is a question. What we are doing here is correct, that you are trying to differentiate function and trying to differentiate inside. That seems it gives a solution to your Laplace equation in Rn, but unfortunately you cannot take that differentiation inside, and that is what we will be discussing in the next, when we can take the differentiation under the integral sign. You need something. Okay. So, let me stop it now and we will continue from here. Thank you.